Okay, thank you all so much for giving me the chance to talk this afternoon, in particular on the first hot day of spring. I timed myself earlier on, I'm going to finish on time so we all get a chance to get a gin and tonic in the sun. So I'm going to be talking about the environmental impact of our built environment. So really I'm going to be focusing on those kind of decisions and project management in the kind of construction and built environment sector. But even if you're not in those sectors, I hope you'll be able to take something useful out of what I talk about. So I'm going to start with what I think is a not very provocative statement, and that is I think buildings are good. Now you might say, look, you're the head of School of Built Environment, you would say that. But look, when we go around the world, we see that there are a few things we can do in society that are more beneficial for people than to build. This is a photo I took in Dharavi in Mumbai about 15 years ago. If you've ever been to Dharavi, it is a location where 1 million people live in a square mile in what could really be called slum conditions. And the United Nations say around the world, 1 in 4 people do not have access to safe, comfortable, affordable housing. So I would go further than say buildings are good. I would say we have a moral and societal obligation to build, to create. The flip side of that is every time we build, it has an impact on the environment. And every single building we create has a negative impact on the environment. Now that's much more provocative, and it's very provocative to, I'm in charge of 4,000 students in my school. They're future architects, construction project managers and more. To actually know this is quite provocative, it impacts me. So we know that buildings are responsible for about 37% of all process and energy-related CO2 emissions. And they come from a number of different places. They come from burning gas inside buildings, they come from using electricity in buildings, but they also come from the materials as well. And the materials we use when we create infrastructure and buildings are incredibly carbon intensive. Cement, for example, is responsible for 8% of all CO2 emissions. 8%. That's double the much maligned aviation industry, for example. And there's not many buildings, there's not much infrastructure we can build without cement. And to give you a kind of flavor of how much concrete and cement we use, this is a fantastic graphic by a visual capitalist, and I hope this is going to work. I'm going to press the button now. What you're going to see on the right-hand side is the amount of materials we use as a human race, and what you see on the left-hand side is nature. And now, if you weigh up all the materials we've created as the human race, it now weighs more than nature. Is that moving? Yes, we're moving. Okay, so what we see at the top is concrete, more concrete, bricks, aggregates, metals, asphalt, other. On the left is all of nature, the entire biosphere. So we are truly in the Anthropocene at the moment. And what I mean by that is we have now dominated nature. We have taken it over. We're in an era where our construction weighs more than all nature. And again, that's incredibly confronting. So those materials we use to create infrastructure, to create buildings, to create cities and more, has an incredibly large impact on the environment. Now we can measure that impact relatively easily, and we do that through something called life cycle assessment. And life cycle assessment is where you measure the greenhouse gases from a product, a building, a process, throughout its entire life cycle. So this is a life cycle of a typical building, and at each stage, greenhouse gas emissions are created or energy is used. So if you imagine a building like the one we're in now, might be a steel frame building. That steel at some point was iron ore in the ground. It was mined out of the ground and transported to a factory. That creates CO2 emissions. In that factory, it would be turned into a steel beam, for example. That creates CO2 emissions. That's transported to site and lifted up by a crane. That crane might use diesel. That creates CO2 emissions. And then you get to the yellow point in the middle, and then you hand the keys over, the building's operated. Lighting, air conditioning, heating, cooling across the building's life. They all create CO2 emissions. Then at some point in the future, maybe 50 years, hopefully longer, hopefully not 20 years, although we do sometimes see that. We're incredibly linear in the way we demolish. The building would be demolished and the materials would either be reused or sent to landfill. And across every point in that process, there's an impact on the environment. The big problem we have in Australia is that's the only bit we measure. We only measure the air conditioning, the lighting, the heating, the cooling. We have no history of measuring all those other parts. Certainly from a building perspective. From an infrastructure perspective, it's a bit different, but from a building perspective, we only ever measure those parts. They're the only bits that are regulated. Everything else is totally unregulated. And so much of my conversation today is going to be trying to open up this idea to you all of life cycle assessment, to think about the life cycle of different processes, and in particular, the life cycle of buildings. So what about embodied carbon, which was in the title of my presentation? Well, embodied carbon was all the blue stuff on that last slide, and it's the greenhouse gases from extracting raw materials, processing those materials, assembling components together, transporting materials, construction and installation, maintenance and repair, and then finally deconstructing or disposal. Sometimes that's not included because that might be 50 years down the line, and so it can be quite difficult or uncertain to measure. And then you've got operating carbon, which is heating, cooling, lighting, air conditioning. So they're the two main categories. Now, if we add those two together, we can work out the carbon footprint of a building, or the carbon footprint of a piece of infrastructure, or the carbon footprint of a product or a process. And from a built environment perspective, if we go back 20 years, what we thought the general breakdown was 80-20. So the general idea, certainly 20 years ago, was that the vast majority of emissions related to buildings and cities were all operational, or the vast majority were operational. And that's why we regulate energy efficiency in lighting. It's why we regulate energy efficiency in air conditioning, cooling, and heating. It's why they're built into our National Construction Code, for example. The latest data, and certainly data of projects we've been working on, suggests currently if you build a building today, here in Australia, you're looking at 50-50. So 50% of the emissions will be in the materials and 50% of the emissions will be in the operation. Now, why has that changed? Well, one, our codes have got far more strict. We put more materials into buildings. We put more insulation in. We might sometimes use double glazing. We've got bigger systems, for example. But at the same time, the electricity we use has started to decarbonise. So today in New South Wales, if you use 1 kilowatt hour of electricity, you will generate something like 0.79, I think, kilograms of CO2. Kilograms of greenhouse gas emissions. That's been dropping year upon year. That's going to continue dropping as we decarbonise our electricity grids, as we move to renewable sources. So at UNSW, we've all the electricity we use is from a purchase power agreement with a solar power plant. What that means is all our emissions are materials. All our emissions are materials. And for the vast majority of new buildings by 2030, that's going to be the case. If we see building regulations change by 2030, which we anticipate will happen, I'm not sure whether it will happen now, there's some uncertainty in there, but we're likely to see this shift where for the vast majority of new buildings will be net zero operational, and therefore all their emissions will be the materials. And that's a really big shift in the way we manage and organise assets and manage and organise the built environment. We've gone from understanding that 20% of emissions are related to materials up to 100%. And we have not caught up with that knowledge change. So the way we do things is still a little bit behind in that sense. So, and actually if you look at the profile, it's quite complicated. So this is what the profile of emissions would be for a new building built today, or built actually 2023 when I put this slide together a couple of years ago. So you create a new building. You've got what's called upfront emissions. So all the materials go to make the building before you hand over the keys, so to speak. You've got a big jump at the beginning. And then you start operating the building, so it increases. The emissions increase a little bit each year. And then after 10 years, you've got to refurbish the building. The carpet's worn out, paint is scuffed, so you have that little jump. That's called recurring embodied carbon, the maintenance of the building over time. And then you continue operating it and the emissions go up. But you'll notice that emissions line, the angle is decreasing. The reason that angle is decreasing is because we're decarbonising our electricity grid. So to run that building today, it takes more emissions than will to run the same building in 10 or 20 years' time, because the electricity generated today is more carbon intensive. The upshot is what we find for any kind of new piece of building created today, 50% of the emissions are likely to be in the materials. Now, why is that important? Think about how much new construction is going on. Now, in Australia, we talk about 1.2 million new homes needed in the next 4 or 5 years. I forget. I'm not going to comment on that too much. It's a pretty provocative number. But globally, there's 96,000 new homes are being built every day. In fact, if you look at what is being constructed every year at the moment, it's the equivalent to all the floor plates in Japan every single year for the next 35 years. It's about 230 billion square meters. That's a lot of square meters. It's a lot of concrete, a lot of steel, a lot of aluminium, a lot of copper. A lot of those materials which we know are quite carbon intensive. And if, like me, and you're slightly unhinged, you can actually calculate the carbon footprint of that. If you've got nothing better to do on a Friday night, that's what happened to me a couple of years ago. And so what you see on the right-hand side is my very basic math. So we know we're going to build about 230 billion square meters of new construction in the next 35 years or so. A typical Australian house has an embodied carbon of 660 kilograms of CO2 per square metre. So if you look at the floor and you imagine a square metre now, to create that square metre would take around 660 kilograms of greenhouse gas emissions. Now, if we create every new building around the world in the next 35 years in the same way, we can do 230 billion times by 660 kilograms. We'd end up with 151.8 gigatons. And that number means nothing to anybody, of course. So let's contextualize it. On the left-hand side, you see the IPCC's carbon budget table. So carbon is cumulative. We can't really take it out of the atmosphere. It just adds up. It's like a bucket of water, and we keep pouring water in. And when you get over a level, then you will have global heating to a certain level. The little circle I've put on the left-hand side says if we want a 50% chance of remaining within 1.5 degrees, we've got a global carbon budget of 500 gigatons. Now, what I just said on the right-hand side is just to create new buildings would be 151.8 gigatons. So 30% of our budget is gone before we've turned a light switch on, before we've fed a human being, before we've built a road. That is inherently unsustainable. That cannot be done. It just doesn't work. And in fact, that 500 number is now closer to 250. I'm very sorry to depress everybody as well, by the way. I just should apologise. I take it down, I take it back up again at the other end. So look, but it is quite confronting, and I am here to confront people. This is incredibly difficult, and for me, this is one of the greatest challenges of the 21st century. How do we square this circle? The math is not mathing. We cannot make that work straight up, but it does say the way we're constructing and the decisions we're making at a construction level and a built environment level are unsustainable. And this graph, of all the graphs I'm going to show you, and I apologise now, there's quite a few graphs in here, this one's probably the most important. This is what I call the building carbon paradox, and the United Nations put this out a few years ago. The red dot is the amount of floor area we build, or anticipated to build. At the moment, we have about 250, nearly 300 billion square metres of floor area around the world, and that's going to grow to about 450. So that's the red dot, and you see that going up. The bar chart is the amount of carbon budget we have to do that. So we're going to double global building stock while our carbon budget goes down to zero. That, for me, is a paradox. Doesn't work. Doesn't work. So we have a bit of a challenge here. And this, for me, is what a lot of my research is involved in, a lot of my colleagues' research is involved in. How do we do this? How do we, on the one hand, create built environments, places to live, work, and prosper for people, because we have a moral obligation to do it, and now, on the other hand, do we do it without screwing over the environment? And that's pretty challenging at times. So for the next 20 or so minutes, that's what I'm going to try and talk about. Some of those decisions that, particularly in the kind of project management and construction spaces, we can make to tackle this. But before I do, I want to set some targets for us as well. So the World Green Building Council have said, to do this, here are some targets. Firstly, by 2030, all new buildings must be net zero operational carbon. What that means is the air conditioning, the lighting, the heating, the cooling must be reduced as much as possible and then offset and use only renewable sources. But it also says all new buildings, infrastructure and renovations will have at least 40% less embodied carbon than today. So we've got to make a 40% reduction on what we've got today, and we've got 5 years to do it. Ambitious, but possible. By 2050, all new and existing buildings must be net zero operational. Okay, we get that. All new buildings, infrastructure and renovations will have net zero embodied carbon. I don't really know what that means. And not a lot of people do know what that means. And that's a very emerging space, because when we operate a building, we can get all the energy from renewable sources. Materials don't work like that. Materials cannot all come from renewable sources because the chemistry of how we create materials does not allow that. For example, concrete, when you create cement, you heat up limestone in a kiln and you rotate it, and the chemistry breaks down and releases CO2. So it's very, very difficult to get net zero concrete, for example. So what about decision making? How should we all consider this? Well, again, this is probably the second most important graph I'll show. When it comes to reducing embodied carbon, the earlier the decision made, the more impactful it can be. The second you decide to build a building, or second you create a building, you say, we're going to build something, and you've locked in 60% of the emissions already. And so this is again from the United Nations, the World Green Building Council, and it talks on the x-axis about the different stages of project development. So you've got planning, early briefing stages, whether you need a building, whether you need an asset, whether you should change it, design, construction and then operation, and then up the y-axis, the amount of carbon reduction potential. So if you want to have 100% reduction of carbon, you don't build anything. And that's great. Can be quite difficult to persuade people sometimes with that one, but there may be some cases, and I'll show you as we go through, where that might make sense. In the kind of design stage, we can build clever, we can build efficiently, but the quote that comes with this, in general, the greatest savings can usually be realized at the earlier stages of a project, really do ring true. It's really, really important. The briefing stage, when there's a discussion and decisions being made about whether we should adapt an existing asset or knock down and create a new asset, that will save more carbon than, for example, using timber or building out of straw, which I'll also talk about as well. So let's start with build nothing. If this happens, I'm out of a job, but look, it is a very effective way of reducing emissions. 100% reduction. Not applicable everywhere, certainly not applicable to housing, for example. It would not go down well. But let's look at the Olympics, for example. The Olympics used to be a good excuse to build a lot of buildings, a lot of new shiny buildings that didn't necessarily get used afterwards. I was just in the AI panel that talked about the Brisbane Olympics apparently going several times over budget. But in LA in 2028, they're very proud of saying, we're not going to build any new buildings. Now, 10 years ago, you'd never get an Olympic saying that. You'd never get an Olympic committee saying, we're building nothing. We've got all the infrastructure we already need. And so that shows you the kind of change of mindset that's happening now. So the Los Angeles can host the 2028 Olympic and Paralympic Games without building a single new permanent venue. There will be some temporary venues, of course, but no new permanent venues. Now, this isn't always possible. Of course, if the Olympics was going to be in Dakar, for example, or if it was going to be in the Middle East, it might not be possible. But in some places, this is possible, and it is now being celebrated as well. So let's put build nothing aside, because we can't always do it. What about build less? So if we build less, we can save potentially up to 80% of emissions. When I say build less, I'm talking about building smaller, more efficiently, and adaptively reusing the assets we already have. So if there's a decision early in a kind of project, we've got this building, it's 20, 30 years old, do we demolish it or do we adaptively reuse it? That's the kind of saving that can be in the 60 to 80% embodied carbon space. And look, after I finished talking to you about crazy things like concrete, you can actually go out to Circular Quay and see a really good example of adaptive reuse. This is a Quay Quarter Tower, completed a couple of years ago over COVID. It was a 1970s office building that had effectively reached the end of its functional life. 45 years old, short lease span, kind of out of date. Normally, 9 times out of 10, that would have been knocked down. Here, there was a planning decision made to move air rights from one site to another site as long as the building was adaptively reused. The architects cut the front off the building, extended the floor plate by 50%, and so they made the kind of financial viability of the project improved by increasing the amount of floor area, and in doing so, they saved about 2/3 of the existing structure and about 8,000 tons of CO2. So this, for me, had a very strategic planning decision very, very early on in the project. And that's what made this happen. But then you've got, really innovative architecture and fantastic engineering as well that kind of make this happen as well. Huge amount of coordination needed at a really complex time as well during COVID. So a remarkable building. Anyone gets a chance to go inside as well. It's really interesting inside in that the building's built out of these villages, which are something like 8 to 12 stories, and they have atrium in them, but you can actually fill in the spaces in between. And so it allows for adaptability. Again, extending the life cycle of the building, extending the potential use of that asset as well. The other thing we can do is build smaller. Again, being a bit provocative here, but we know here in Australia we have some of the largest houses in the world. This is a diagram that shows different house sizes in the world. So the average house size in Australia is about 214 square meters. In Hong Kong, it's 45 square meters. Now, there's obviously differences in demographics and other things that play there as well, but one of the simplest ways you can reduce emissions is to reduce the size of not just housing, but any kind of building, any kind of asset. Do we need all this floor area? Should be one of the really important early decisions and questions asked of any project. What do we need? What is sufficient? What is essential? And one of the things we'll see, no doubt, with this shift from detached houses to apartments, apartments tend to be a lot smaller than detached houses. They have a higher embodied carbon per square meter, but a lower embodied carbon per person dwelling in them, because people are generally willing to accept smaller floor areas in apartments in exchange for proximity to amenity, to parks, to places of work, and to other cultural facilities as well. So, then we can build clever. By building clever, what I mean is dematerializing, using fewer materials, but also being smart about the kind of materials we use in the first place. And look, I consider most buildings like, and this is a weird analogy, so bear with me, I am going somewhere, like a kind of like if you break your arm and you put in a cast, right? And the cast is very functionally effective. It stops your arm from moving, so it does its function, but if it's itchy, you've got to stick a pencil in there. It gets a bit awkward. But it's functional, but it uses a lot of material. What we need to do is to do something a little bit more like this, where we're actually really using technology and using strategy to really think about what materials we need and where. So the benefit of the one on the right is it uses less materials. It's probably been 3D printed, so a bit more expensive there, but also it's less itchy. You can kind of scratch it easier as well. So you've got a functional benefit and you've got a material benefit as well. And look, we're seeing this in the built environment. You imagine a typical, without turning this into a structural engineering presentation, a typical beam in a building is designed because it's easy to build. But a lot of the material in that beam is not doing anything structurally, like the one on the left-hand side. We're starting to see products emerge like this is called the mini-mass beam, where it's 3D printed concrete, where the material is only in the places necessary to carry the load. It's more expensive because it's not as quick to build, and it's more kind of requires printing, but it has potential up to 78% less concrete in there as well. So as these things become more commercially viable, we will see ideas like this emerge onto the market as well. The other thing as well is to think about columns. Now, this is, again, a bit of a weird kind of one, but one of the things we find with embodied carbon in buildings is the floors that are the big contributor to emissions. So of all the materials in a building, actually keeping the floors where they are, the beams and the slabs, that's the biggest contributor to emissions. And to reduce that material, we can actually add in more columns. Reduce the lease span. Now, this reduces the commercial viability of spaces, because if you imagine this space here, I could reduce the embodied carbon by putting a line of columns down the middle. It's going to mean some of you can't see me. It's going to have a bit of an impact. It's not going to be commercially viable, but it will reduce embodied carbon. So what we can see from this graph is the span in meters along the X and the embodied carbon along the Y. An 11-meter span in a building will have a typical embodied carbon of 250 kilograms of CO2 per square meter, whereas a 7-meter will drop down to about 150. It's an enormous reduction of emissions, but it requires those early conversations with the stakeholders, with the client, to say, hey, you've got this space. Can I put some columns down the middle of this space? Are you going to be able to operate in a normal way if I do that? Can we organize the furniture and the layout of your space so that the column's not a problem? Because this will save more energy and more emissions than making the building out of timber or putting straw in the building or putting solar panels in the building. This kind of decision will save a huge amount of emissions. And it goes further as well. This is the next slide. This is a beautiful skyscraper in Italy called the Intesa San Paolo Tower in Turin. It's by a world-famous architect. It's a very, very beautiful skyscraper. To give back to the public, they've created this multifunctional kind of amphitheatre underneath the building. Now, I don't know if you've ever been to an amphitheatre. You do not want columns going through that. So to transfer all the stress of the floors above, they've created the big red truss that you see there. And so the whole idea of that is to take the kind of forces from down the building and to transfer it around that kind of space. Now, that requires 2,350 tons of steel. That will have an embodied carbon of about 6,815 tons of embodied carbon. And so you have a public benefit, multifunctional public space, and an environmental cost. How do you weigh those two up? And these are the kind of early stage decisions that we will be making much more into the future. Now, you could argue, could you take that multifunctional space and just move it out from underneath the building? That would have been one solution potentially, but you can't bring the columns through. So sometimes you're going to have these kind of technical challenges, but really they're not necessarily technical challenges. This for me is about a conversation and about building it into the project management kind of lineup very, very early in the design, in the kind of decision-making processes about, hey, there's a trade-off here. There's a public benefit, there's an environmental cost. Do we want to own this environmental cost, or is there another solution to this? The other thing is, look, I talk a lot about structures, but it's not just structures, it's also the stuff that goes into buildings. There's two types of embodied carbon. There's upfront embodied carbon, it's to build the building in the first place, and then there's recurring embodied carbon, that's to maintain the building over its life. So if you think about the structure of a building, that hopefully lasts through the whole building's life cycle. If it doesn't, something has gone wrong, talk to your lawyers. However, the stuff that goes into a building will be replaced. You think about the carpet, that carpet will last 5 to 10 years because of footfall. So over a 50-year life cycle, the structure might last 50 years. The carpet will be replaced 5 times. So its emissions will cumulatively add up. And what we actually find is things like fit out and finishes, those things that are quite small at the beginning. Once you add them up over time, their emissions can be really, really large, and actually larger than the structure as well. So solutions to that are things like dematerializing fit out. Do we really need suspended ceilings? Or can we expose all the surfaces and make them look funky? The benefit of this is it can reduce cost as well, which is beneficial for the client, but it can also reduce emissions at the same time. It might increase the maintenance schedule for kind of dusting some of those spaces as well. So again, it's about having those early decisions in the process, in the development process, to understand the pros and cons, the environmental, the economic, and the maintenance kind of decisions as well. And look, and central to this as well is efficiency is sustainable. And this is something I talk a lot to the students about and a lot in my research, in that the more efficient a building can be, we can get the benefit of increased cost, increased rent, but also reduced materials. So this is 2 different office buildings, the same footprint. one of them has a smaller core, so it's more compact in the number of elevators, the number of stairs it has, the number of services, but they're the same building. Now, they may have the same embodied carbon per unit gross floor area. I've estimated about 700 kilograms of CO2 per square meter. But because the building on the right delivers more functional area per unit person or per unit functional area, per unit net lettable area, it will have a lower embodied carbon. Because across that company, they may need to build fewer buildings, for example. So again, it comes down to really questioning early on what is sufficient, what is necessary, what is enoughness, how much of something do we actually need, and how can we make it more efficient accordingly. I bet you never thought I was going to show you a food pyramid. I noticed they are having a food expo down there, which I spent 10 minutes walking through on my way here getting lost, so I probably should have gone in there. But look, if like me, when you went to school, you were shown the food pyramid and you were told, look, there's foods at the top, you know, the lollies and the chocolate, you can have a little bit of, but don't have too much of. And there's foods at the bottom, the kind of cereals and the fruits and vegetables you should have more of. And really, we should all have a balanced diet. Wait there, I am going somewhere with this. Buildings are the same. So you can do a food pyramid for building materials. The materials at the top have a very, very high embodied carbon. Things like copper, zinc, aluminium, they are very carbon intensive per unit material because they require a lot of energy and a lot of emissions to create. And then you've got things like steel, paint, and ceramics in the kind of middle, and at the bottom you've got biomaterials, things like timber, straw, hempcrete, and other things which have a lot lower embodied carbon. And so when I show this, I'm not saying, hey, look, we need to build everything from the bottom. What I'm saying is we need a more balanced diet in our cities and buildings. We need to try to use more materials from the bottom and only use the ones from the top where we absolutely have to as well. So I've got about 10 more minutes, and so I want to show you two projects we've done at UNSW that kind of explore some of these ideas. And the first one's called How Low Can We Go? It's a collaboration between UNSW, UTS, and Terroir Architects. And we really just wanted to ask the question, well, how low can we make embodied carbon of an asset? You know, what kind of decisions do we have to take, and how low can we make it? How much can we push this, and what kind of technologies, ideas, and decisions do we have to look at? And we were lucky because Terroir had just completed a timber high-spec office building in Tasmania. It's a building with the red dot around it. So it had a recycled ground floor. We used a lot of reclaimed brick and a lot of existing materials from on the site. Then it had a timber frame. So used a mixture of glulam and CLT, which is cross-laminated timber, very low carbon, a concrete core, and a curtain wall facade. And we called that the BP model, a best practice. We then designed a concrete version of that, which was much more typical of standard Australian office buildings, called the TY. And then we went a bit mad with our two stretch scenarios. So the stretch scenario is on the right-hand side. So we created an all-timber version, which is called ST/STR. And in that one as well, we added more columns. We designed out all the beams and we added more columns. So the typical building had a column grid of 9 by 6. So it had a really open plan office space. Clients very happy. The one we redesigned was 3.6 by 6. So it had a line of columns straight down the middle of the office space. The kind of thing that might not be commercially viable, but would require that very early stage conversation. And the one on the far right-hand side, we changed all the curtain wall and used recycled materials. We put straw in the facade. We threw the kitchen sink at it effectively to see every possible lever we could pull to reduce the emissions. Now, what we found is through absolutely everything, we could reduce emissions by a maximum of 45%. So what that means is the second you've decided to build a building, you've locked in about 55 to 60% of emissions. It's pretty commercially unviable to create a building with straw in the facade in Australia at the moment, but so even so, you're more likely looking at 30% saving. And so we managed to get up to 45%. The interesting thing for me was the change from concrete to timber only saved about 10 to 15% of emissions. So timber is heralded as this big sustainable material, and it is. All the evidence shows it is lower embodied carbon than concrete, but it's not going to save us. We can't timber our way out of this mess, I'm afraid. It will save emissions, but it had its biggest effect when we also increased the number of columns, reduced the beams, put a flat slab in, and reduced the floor-to-floor heights as well, so we can make the whole thing a lot more compact. And that's when we could save about 35% of emissions. And then this graph, this waterfall graph, shows every decision we took throughout the kind of process and what were the emissions. And the really interesting thing for me was the most effective strategy was removing the carpet. So we had all these expensive architects and structural engineers and researchers around the table, and the biggest saving was taking the carpet out and putting a hardwood floor in, because the carpet was being replaced multiple times over the building's effective life. And so, you know, what this says is it's not just those early stage decisions, it's the little things that count as well. It's being cumulative. It's thinking about all the little things that count across that kind of project process that will reduce emissions. The second most effective strategy was actually putting a timber curtain wall on there. So we found a kind of hardwood curtain wall, which we put on there. And the third most effective strategy was switching from concrete to timber and changing the column grid as well. But we also asked the question, we said, well, look, timber's got this benefit, and that timber stores CO2 emissions. Can we use that in a way to get down to net zero? So I said earlier on, we don't really know what net zero embodied carbon is. We said, can we fudge this? Can we make this happen? So one of the things, without turning this into a chemistry lesson, you never thought you'd get photosynthesis in the food pyramid in a lecture, did you? Trees photosynthesize, they absorb CO2, they release oxygen. That CO2 is captured within the woody biomass temporarily to the end of the timber product's life. And so what you see on the right-hand side is a graph of this. Timber's a blue line. As a tree grows, it absorbs CO2, so it has a negative emission, and then you cut the timber down, and across the building's life, it stays static. At the end of the building's life, if you burn that timber, all those emissions go straight back out into the atmosphere. If you landfill that timber, it slowly releases as methane. Concrete is the yellow line. Concrete's kind of the opposite. It creates a lot of carbon to create a concrete product, but then over the concrete's life, concrete actually absorbs CO2 in something called carbonation. And at the end of the concrete's life, if you smash it up, it absorbs more CO2. So we decided to factor some of these things in. And what we found is actually, if you count the carbon stored in the building, we could get down to net zero embodied carbon in an office building, but only temporarily. So the graph you see here is over time, and there's enough biogenic carbon stored in the building at the beginning to make it net zero for 19 years. And then the maintenance builds up a little bit. But you see that little thing at the end? That's all the emissions coming out when you burn the timber at the end of a life. You can sometimes call that the carbon burp, because, you know, all these emissions come out later on. Now, it relies on a lot of uncertainty. What's going to happen to a timber beam in 50 years' time? Are we going to be burning it? Are we going to be landfilling it? Are we going to be reusing it again? Huge amount of uncertainty in there. But we have to assume the worst-case scenario because we are the human race, and so we assumed we would burn it. Potentially, if we reused it, it could maintain its benefit over time. But we do find that a bit perverse as well, because one of the things we looked at, the building had slabs which were about this deep, 250 mil. If we made them double, and we don't need to do that, if we added all this extra unnecessary timber, the emissions went down, because you're adding in more storage into the system. And so you could end up, a very unscrupulous person could add a lot more timber into a building than necessary to get a better environmental output. That goes against the fundamentals of resource efficiency as well. So within a lot of these kind of mathematics and a lot of these metrics, you can fudge the system, you can manipulate the numbers, you can use what we call creative accountancy on carbon emissions as well. So another lesson here, be wary. Be wary of anyone who says anything's carbon neutral or net zero this or negative that. Really look at the numbers, because it depends. But then we went a bit further and we said, okay, look, can we get all of Australia's buildings down to net zero by 2050? So we modelled using something called the ISGD model, which my colleague Cameron Allen, or my former colleague Cameron Allen, developed. We took all the buildings in Australia and modelled them across the next 50 years. And we used 3 scenarios. So we had business as usual, which is typical temperature increases, typical resource demands. we assumed 30 to 50% of buildings would be electric by 2050 and 60% of renewable energy by 2050. This is what we expect to happen. Then we had two stretch scenarios. Stretch scenario 1 was lower temperature increases and lower resource demands, 70 to 80% of all electric buildings by 2050, and 80% renewable energy by 2050. And scenario 2 went even further. Basically, we said there would be a really ambitious energy efficiency investment, 100% electric buildings by 2050, and 100% renewable energy by 2050. And we said 30% of all buildings will be made out of timber, slowly over time. So 1% in 2021, 2% in 2022, 3% in 2023. So we added it up. So we assumed there'd be this massive shift in the way we build. The model was very sophisticated. It was a top-down model. So instead of saying we're going to build this many houses, it actually models economic input-outputs. And so, for example, we know as people get wealthier, they buy bigger houses. As GDP goes up, we build more offices. So that was the algorithm that was in there. So this is GDP over time. You can see the lovely little blip for COVID, which we all try and forget now. But the thing to really pay attention to is that by about 2040, we're modeling GDP leveling off because of urban heating. So productivity losses due to climate change, due to disasters and other issues that we're going to face. So the model was sophisticated enough to build those things into it. This is operating emissions by 2050, and you see business as usual will be 59 million tonnes, whereas scenario 2, where everything's renewable energy, would be pretty close to zero. The really interesting one, though, is the next one, which is embodied carbon. And so what we showed there is business as usual will be 4.3 million tonnes. But in scenario 2, in the timber scenario, we would actually get down to net zero embodied by 2042 and then go into net zero negative kind of territory. And that's because the actual building stock was absorbing or had absorbed and was storing more carbon than was necessary to create more buildings as well. So that was, again, using that kind of ability of timber to store carbon to effectively, with the city and our infrastructure being a carbon sink, a temporary carbon sink. And overall, we got pretty close to net zero overall, but with some adjustments, we felt it was possible. So I know I set things up on a very depressing note, but some of our modelling shows that with relatively radical changes, we can get down to net zero by 2050. So in conclusion, for most new buildings, embodied carbon will be the largest contributor to total greenhouse gases in the future, at least 50% we expect. There's strong evidence that embodied carbon can be significantly reduced in the built environment today. I think 40% is achievable in the vast majority of buildings. And often there can be cost benefits as well to that. Taking materials out of buildings, being strategic about whether we need buildings and whether we need floor area can save cost as well. But decisions made earlier in the project, i.e. whether to adapt existing and reuse existing assets or to improve floor space efficiency, for example, that really need those early stage conversations will have a more significant impact than changing materials. Again, we can't just change our way to timber and get out of this mess. Thank you very much. For those interested, that's a QR code to a couple of articles about this. And I think I've got a couple of minutes to answer any questions if there are any. Thank you.
You do indeed. Professor Oldfield, thank you very much indeed. You did manage to turn it around. I thought at one point we were all going to hope for a demise before 2040, 2050, but things are looking up for our children and our children's children. Just a moment.
Thank you very much. That was a very engaging presentation that I wasn't expecting to enjoy as much as I did. I'm just wondering, the building that you referred to in Circular Quay where they sort of stripped down and reused the concrete core, what kind of impacts did that have on their build budget and schedule? I'm assuming it costs more and takes longer. And also for the building where you've got straw and timber in the materials, what kind of safety impacts does that have in terms of fire safety?
They're great questions. So for QQT, I am not privy to their build cost, but one of the things we find with adaptive reuse is it's probably 40 to 60% less emissions, but the cost is often the same as new build or even higher. Now, we see that, for example, lots of people talk about office to residential conversions. You know, we've got all these kind of grades B and C assets out there. Can we just convert them to apartments? Now, take the architecture aside, one of the big barriers is cost. Because the second you start stripping back a building, you find asbestos, you find all these other kind of things. And that's often built in as uncertainties. And so often you can find adaptive reuse can even be 20% more expensive than demolish rebuild. That's one of the big challenges, and that's why I think we need to incentivize through tax breaks and through other mechanisms to make that viable. Otherwise, it's just not going to happen. It's going to be extremely challenging. I think I was actually giving a presentation with the architect of that building earlier in the week, and he talked about in the early stages of the project, they didn't talk about it being adaptive reuse because adaptive reuse wasn't sexy. You know, it wasn't seen as a sellable thing. But now I think as we become more green savvy, you know, there may be benefits to adaptive reuse in terms of rentable area, in terms of, you know, kind of rentable value, and that's where we might see the kind of asset price change. Now, in terms of those other buildings, in terms of safety, so timber, we built in additional timber for what's called the charring layer. So if you imagine a forest fire, trees get burnt. Often the trees don't die. It's because the outside of the tree chars. That char creates insulation that protects the inside of the tree. A timber structure can work in the same way. For the straw in the facade, we gyprocked it in to effectively keep it away from any kind of fire hazard, potentially. But that did increase the amount of materials in some ways as well.
Lovely, thank you. Any other questions? It's always right up the back, isn't it? Okay, I'm going up here and then I'm coming back to you. Such good exercise.
Thanks. Just a quick one on the detail of the graph. Why are we projecting a productivity decline in the 2040s?
So that was due to the model had a certain number of algorithms built into it about GDP and productivity. And it also predicted that we would face global warming. And as global warming increases, we'll have greater disasters. We may have greater increases in weather events. It might get more difficult to work inside potentially, could increase energy bills. It factors all those things in as a potential productivity decrease at that time. But with any projections, there was a huge amount of uncertainties involved in that.
Thanks. For last one over here.
What's the timing of the changes to legislations, building codes and standards that's going to really drive this?
Well, I originally put this lecture together before recent announcements. Look, there's obviously going to be a 3 to 4 year pause. I think we wasted much of the 2010s. To be honest, we sat very static in terms of legislation across the 2010s. We're increased to 7-star NATAs now. During that time frame, Europe switched to net zero operating. So all new homes built in Europe, now in the EU, have to be net zero ready, which is higher than 7-star NATAs. So we are anticipating a few things happening in the future in the building code. One, at the moment in New South Wales, you do have to measure embodied carbon, but there's no cap. I anticipate in the next 5 to 7 years there may be a cap. You go somewhere like France, there's a cap on embodied carbon per square metre, and that cap reduces every 3 years. So I anticipate probably early 2030s we'll see a cap on embodied carbon. I also anticipate at some point all new buildings will be net zero operational. Whether that will be the 2030-esque kind of NCC or further, I'm probably the wrong person to answer that.
Nice curly one to finish. Professor Philip Oldfield, thank you very much. What an entertaining way to complete day one.